Hello friends, my name is Tom and today we're going to talk about the SR Latch. Before we get into this topic, I think it's important to note the difference between combinational and sequential logic. Combinational logic are devices in which the output of the device depends on the current input value. Take an OR gate in which output C is high when A or B are high, as seen in this truth table. Or the AND gate, in which output C is high when A and B are high. Or we could take the complement of these with the NOR gate. When A or B are high, then output C is 0. The only case in which C is 1 is when A and B are 0. Or with the NAND gate, when A and B are 1, C is 0. All other cases, C is 1. Now, sequential circuits are devices in which the output depends on the present value of the input as well as the input's previous value. And that's where our conversation is going to go today with the SR latch. Now let's take a look at the NOR SR latch. This device is made up of two NOR gates. Gate 1 has input R and output Q. Gate 2 has input S and output Q naught. Each gate has its output fed back into the second input of the other gate. Let's assume that on power up, this device has outputs Q equals 1 and Q naught equals 0. First, we're going to look at the case in which both S and R are set to 0. Gate 1 would have inputs 0, 0, and output Q equals 1, as seen in the truth table. Gate 2 would have inputs 0 and 1, and its output Q naught would be 0. So when both S and R are set to 0, the next state of Q, denoted by Qn plus 1, is the current state of Q, Qn. Next, we'll consider when R is set to 1. In this case, gate 1 would have inputs 0 and 1. Q would therefore be forced to 0. Gate 2 would then have inputs 0 and 0, and Q naught would be forced to 1. So when R is set to 1, the next state of Q is 0. How about when R is returned to 0? Well, we already saw before that when S and R equals 0, the next state of Q is the current state of Q. So the device remembers, and it's 1-bit memory. Now this is really important, and we'll find that this is a very fundamental building block for digital logic design. How about when S is set to 1? Gate 2 would then have 0 and 1, forcing Q naught to 0. Gate 1 would then have 0, 0, forcing Q to 1. So the next state of Q would be 1. Now how about the last state, in which both S and R are 1? Now in this case, gate 1 would have 0 and 1, and that would force Q to 0. Now this is actually not a desirable state, because in the event that both S and R return to 0 at this same exact moment, we'd have no way of knowing which output, Q or Q naught, would go to 1. Because of this property, this state is commonly not used. Let's take a look at the NAND SR latch. This device is quite similar to the NOR variety, but this time notice that the inputs are not S and not R, signifying inverted logic. Also note that not S is located on gate 1, while in the NOR variety, S is located on gate 2. First, let's consider the case in which both inputs are 1. Gate 1 would have inputs 0 and 1. Q would therefore be 1. Gate 2 would have inputs 1 and 1, and Q naught would therefore be 0. So when both inputs are 1, the next state of Q is the current state of Q, Qn. Next, let's look at when not R is set to 0. Gate 2 would have 0 and 1. Q naught would then go to 1. Gate 1 would then have 1 and 1. Q naught would go to 0. So when not R is set to 0, the next state of Q goes to 0. Again, similar to the NOR variety, when you return S and R back to what we call the memory state, the output does not change, and it remembers. How about when not S is set to 0? Gate 1, you'd have 0, 1, forcing Q to 1. Gate 2, you'd have 1 and 1, forcing Q naught to 0. So when not S is set to 0, the next state of Q is 1. Finally, we'll look at the case in which both inputs are set to 0. This would force both outputs to be 1, and in the event that both S0 and R0 are returned to 1 at the exact same moment, it would be impossible to predict which output would remain 1. In the real world, it would actually depend on which input returns to 1 first. For this reason, this combination is not used. Alright, and here we have a NOR SR latch built up on the breadboard. You can see that when R is pressed, Q goes to 0. When S is pressed, Q goes to 1. And here's a little demo of when both inputs are pressed at the same time. Well, that's all for today. Thanks for watching my video, and if you want to see more, please feel free to subscribe.